Good evening. Tonight we're going to talk about limits. Okay, so in this case, we are going to think of a limit as being the y part, the value of the y part. Okay, so is the value of the y part of a graph. Okay, so so we might have some graph here. Okay, all right, and as we're getting to some x value, okay, some x value, and I'm going to call that value x equals some constant, okay, c. All right, so as we're getting closer and closer, ever closer to this value from either the negative side of it or the positive side of it, okay, we're getting closer and closer to this number. Then, and by the way, this number could be 0. X could be, it could be x equals 0, no problem with that. Then what we say is the limit as x approaches, say, this number 0, this number 0 of f of x, okay, the function, the limit of the function, as x approaches 0 equals some number L. And that number L would be the value over here, wherever we are, the plus x-axis, plus y-axis, and this would be L. Okay, so the value of y part of a graph as we get to some value of x, okay? That would be what this limit is. All right, so the fun part about limits is that we get closer and closer to this x equals c value, the c value, okay, some number, but we never actually get there, okay? So I would like to just state that we get closer and closer to this x equals c, okay, number, but we never actually get there. Okay, so interesting. Some people like to think of this as an asymptote. Okay, so in other words, you get closer and closer to the asymptote, but you don't actually arrive there ever. Okay, so that could be one way of thinking of it. And so when we're dealing with this, right away we're going to run into this situation where many times we're going to see as a number, as x approaches some number, okay, that and when we have a rational, for rational functions, okay, functions, which would be something like fractions, okay, fractions of sorts, okay, where you have ax squared plus bx plus c or something over ax plus b or what have you, right? So this would be your f of x, just showing you some example here. All right, there's a rational function like fractions. All right, many times we run into a problem where the denominator, okay, of can go to a value, can actually go to a value of 0. Okay, and if that occurs, then the entire fraction blows up. Okay, the fraction blows up is a word. So basically, as you goes to 0, it goes to what? Undefined, right? So you can't have the denominator of a fraction go to 0. So this can't happen. So when we have that problem, it's undefined. Okay, the function becomes undefined. So f is undefined at this place. All right, so that introduction of limits brings us to the first leg of learning about these things, and that would be the case of what we refer to as a removable discontinuity. Okay, so we'll get to that in a second. AKA, also known as holes. All right, so you may say, well, what's a hole? Well, okay, so look at our function here. That looked beautiful. Well, what if the function now looked like this, where at one particular point, for some reason unknown to us, this function, or maybe known to us, but for whatever reason, this value here, as where x equals c, is a hole. So in other words, if this function were continuous, I could trace out with my pen this function, and I would be able to not stop but go right through it like we have in the above example. I would trace this function out with my pen and keep going. So this is a continuous function. You see, this is called continuous function. Over here, it's discontinuous, means not continuous. So I would have to actually lift my pen up to get over this hole and keep going. Okay, so it's discontinuous function because of this discontinuity. Okay, so it's removable, and it's going to be quite trite for you to see what I mean by removable, but in a moment I'll show you. So AKA holes. They call them holes. It's a hole in the function. Only at this one point. And as you know, a point is almost an infinitely small location on the function. So it's very, very small. And some graphing packages won't even show it until you actually come upon it. All right. So let me give you an example then. Here I'm going to have an example of a function. All right, I'm going to try to turn this over and do the example on this side so we're not pressed for space. Okay, so here's an example. I have a limit, okay, of x to the third minus 1 over x minus 1 as x approaches plus 1. Okay, so I have this limit. Now, if I put plus 1 in here, you're going to see right away that I can't do this, because watch what happens. I have 1 minus 1. That's okay. We get 0 up here. But now I'm going to have 1 minus 1 down here. Now, I don't know. We cannot have this in the basement. This up top is okay, but this is undefined. See? So it's undefined, and that's the basis of what we're getting at. So I can't solve this. There's no limit. But there's a trick around removing the discontinuity here, and I can get to the limit. Watch how this works. All right, so if you are very astute, you would have recognized that this was a cubed minus b cubed, the difference of cubes in the top. And the way that got resolved was this would be a minus b a squared plus a plus b. Okay? AB plus b. There you go. So that would be your difference of cubes. So when I put this back in, now my limit becomes this. Plus 1. And I have x minus 1. Okay, I'm recognizing that's a. And this would be, see, what I'm seeing here is this. I have x cubed minus 1 cubed, you see? And that's what I have up top, even though it's kind of showing itself as just x minus 1. This is in the top, the numerator. Okay, so I have x minus 1. When I use this formula, I resolve the top, and it becomes x squared plus x plus 1. And the basement didn't change, x minus 1. So I factored this out. I factored this using this equation here, recognizing the difference of cubes, and then I get some cancellation. I get these two factors to cancel. And so now my limit is, as x approaches plus 1, is simply x squared plus x plus 1. Okay, let's take a look. Put it in. That's 1 squared plus 1 plus 1. So I actually get this limit is equal to 3, plus 3. And there's your answer. So what occurred here was, if you looked at this on a graph, it would be something like this. Okay, and at this value of plus 1, okay, there's a hole. But as I kept going, okay, from the left side and the right side, it all looks like it comes into 3. But it's missing. But I could remove that hole, as I did. I removed this by factoring it out, and what did I get? I got the value that would have been there had this hole not been there. And this is called the removable discontinuity, or hole. And I actually evaluated the limit at that x value, where I couldn't have done prior to that. So there's your introduction. We'll keep rolling with this if we can. Thank you.